In finding the electric field using Gauss formula, E equals to Q enclosed by epsilon naught A is applicable. In the formula, epsilon naught is the permittivity of free space. A is the area of Gaussian surface and Q enclosed is charge enclosed by Gaussian surface. The equation can be used in which of the following situations? Only when the Gaussian surface is an equipotential surface, only when E is constant on the surface, for any choice of Gaussian surface, only when the Gaussian surface is potential and E is constant. So let us see. It is directly saying that in finding the electric field using Gauss law, the formula Gauss law formula E vector equals to Q enclosed by epsilon naught A. So basically the Gauss theorem that we have, that is saying that integral of E vector dot ds vector equals to Q enclosed by epsilon naught. Now what they have did here in the question, they have taken E constant, then only they have wrote integration of ds as Q enclosed by epsilon naught, and then E ds integration will give you area, so A cube enclosed by epsilon naught. So E is basically cube enclosed by epsilon naught times A. So under what condition I am just converting this expression to this expression? When I assume E is constant on the Gaussian surface. Okay, E is constant means not in the sorry, I'm saying E is constant. I will be saying that E vector at all the points on the Gaussian surface has the same magnitude. This is the first point. And second point is that E vector has to perpendicular to the Gaussian surface, so that it will be along the area vector, and E dot ds will become simply E times the total area. So only when the Gaussian surface is equipotential surface, if the Gaussian surface is equipotential surface, electric field is perpendicular to it. But this statement is not giving us any clue regarding the uniformity of the electric field, whether the electric field is uniform or non-uniform. So this option is not correct. Only when E is constant on the surface. So this option is saying E is constant on the surface. That is true. But again, in this one part is missing, that the electric field is distributed in what manner? Is it at any angle theta or theta equals to 0? So again, this is or theta is 90 degrees. So again, this is not a perfect statement, a correct statement, partially correct. For any choice of Gaussian surface, we can have any choice of Gaussian surface there, we can apply, but there is a problem that we should know the area of that Gaussian surface. So any choice of Gaussian surface we are free to choose. Like suppose I choose a Gaussian surface like this way. Now we cannot calculate its area. Only when the Gaussian surface is equipotential and electric field is constant on the surface. Yes, the portion which was missing in the first and second statement, they combined these two statements, and then this has become a perfect statement corresponding to this condition, that we have taken E out and E dot ds is basically EA, that means E vector is along area vector. So electric field is constant and the surface is equipotential. So surface is equipotential, that means electric field is perpendicular to the surface. So both conditions are satisfied. So correct option is option 4th here.